Om Namo Bhagavate Vasudevaya. Good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. Today we are going to discuss a new topic, that is one-dimensional linear harmonic oscillator in quantum mechanics. So before we have to start our discussion in detail, whatever I written in the note, I am going to be give you some two to three examples or idea about oscillator, or when a system or when a particle is going to be oscillate, why it has to be oscillate, and at the time of oscillation how the potential energy is going to be stored. That I am going to be represent with the help of this system. You just watch it. First you see that this is a spring which is attached with a mass. Okay, so this is a mass which is attached with a spring having the spring constant K. Now if this mass is going to be displaced towards positive x-axis direction, initially it is at equilibrium position, let that is at x is equal to 0. This position is suppose at origin, that is x equal to 0. So this is your positive x-axis direction and this is your negative x-axis direction. Suppose this mass is displaced small distance dx along positive x-axis direction. If it is so, then a restoring force is going to be induced inside this spring, which tries to pull the mass towards its original position. I am going to show you a simple example. So this is the situation that a mass is situated at the origin. So if it is displaced somewhat distance, a restoring force developed or induced inside the spring which tries to pull the mass towards its original position, right? So actually this is not the spring only. For this instrument I can only show you one dimensionally, but if it will be spring, then when it will be coming back, it can be moved in this direction and again it will move in this direction. So it will be oscillate about its mean position. Okay, here one thing you can recognize, that whenever we are moving positive x-axis direction, the restoring force, suppose that is represented by RES, is induced inside the spring along this direction. So in which way the displacement we done just opposite the restoring force induced. If suppose this is a spring, if I will press this body towards this side, means negative x-axis direction, if the displacement we are going to be consider, the restoring force will be developed inside the spring which will be towards the positive x-axis direction. The restoring force will be just opposite to the displacement. Okay, this one thing we have been observed. That means the displacement and the restoring force direction are opposite with each other. Okay, now one thing you have to observe, see, this is your equilibrium position. And one thing that another thing is that the restoring force always tries to return the body to its mean position. It tries to pull back the body to its mean position. So you see one thing, that this is suppose the original position at x is equal to 0. You just mark this point. Okay, this point suppose the initial position, this one. So at this situation, from this situation, if I am going to displace this body to a certain distance, I done some work. Okay, I done some work against this restoring force. Only for that I able to displace this object up to a distance, right? So how much I have been done the work, exactly that much work or that much amount of work is stored as a energy inside this spring. So how much work I have been done to displace this object from its mean position to another position, that much amount of energy will be stored in this spring. So whenever I will be leave from this position, that energy converted to the kinetic energy. So how much work I have been done to displace the mass from its original position to another position. Suppose this position is 0 and this position is A and this position is B. Suppose from origin to A I displaced a small distance dx and I done some work against the restoring force. That amount of work has been restored as potential energy inside this spring, and that potential energy converted to kinetic energy like this. Okay, another thing, I displaced this much distance from 0 to A. You just observe the force, restoring force, this one. I displaced somewhat large distance, that is from 0 to B. You observe the force is larger. Okay, that means if I displace the longer distance, then the restoring force will be increased. For this distance, what is the force? For the distance, if I will be increased from A to B, the force will be increases. If I will increase further the distance from 0 to this much distance, the force will be again increases or larger as compared with A and B. So here we found that the restoring force is proportional to the displacement, and the restoring force always opposite to the displacement direction, or we can write the restoring force is proportional to minus x means it is proportional to the x but opposite direction to the displacement. So restoring force can be written as some constant minus x or minus kx. Here k is nothing but called as the spring constant, Okay, so here if the potential energy developed, you just listen carefully, if the potential energy is developed due to some force or due to some work done, okay, due to some work done, the potential energy is induced or stored. Here work done is equal to, magnitude is equal to the potential energy stored inside this spring, but the work done or the potential, how it has been developed or who developed that one, the agent is the force. So here if a central force will be act on a particle or on a body, the body will be vibrate about its mean position. Here this is the center, this is the equilibrium position. You just mark this point, okay, you just mark this point. So this is the center or this is the mean position or equilibrium position. Actually this is not the spring. If I will be drag this one, it will be moved back and move towards this side also. That means how much potential energy will be stored, that much kinetic energy it will be conserved to the kinetic, it converted to the kinetic energy and it will be moving back this side. Again the restoring force direction will be reverse and again it will move this side. That means this particle will be moved about its mean position. That means a force is the so-called central force, means acting towards one center, means it is trying to settle that body towards its mean position. Always it is attracting towards the mean position. Okay, only for that the body is oscillating about its mean position. And in our this is the example of classical mechanics. So how it is useful in our quantum mechanics? So quantum mechanics means we have to consider the microscopic particle, that is atom and molecules. You just consider a simple example, that is one atom, nucleus, and around it electron is there. Another atom, nucleus, and around its electrons are there. So they are formed a bond, or we can call this is a diatomic molecule. So this positive will be attract the negative cloud electron of this one, or they are sharing the electrons, and we can say, and along this bond this positive can be attract this negative cloud, this positive will attract this negative cloud. Due to that they can come closer. Again this positive center is going to repel with each other, then they can move this direction. That means if this is the center of mass of this diatomic molecule, then these two atoms are vibrating, always vibrating about its mean position, That means if I am going to consider this will be the constant, it will vibrate about its mean position, and if this will be constant, that means both is vibrating about its mean position. Okay, now another example you can consider, suppose you consider the hydrogen atom, like, okay, hydrogen atom, the center is plus and around this is the electron. We are considering one dimensional oscillation, so one dimensional you consider. This is suppose your Bohr radius. Bohr radius means at this distance from nucleus to at this distance, the electron probability density is more. So electron probability density is more at the Bohr radius. That is not mean that electron we could not found this area and this area. So electron probability density will be more at the Bohr radius, but it is less beyond the Bohr radius and less than the Bohr radius. That means it indicates that the electron density, if I am consider only one electron is fluctuating from its mean position. Actually Bohr radius is the mean radius, or the average radius, average distance of the electron from the nucleus in one state, right? So this radius is always fluctuating. Only for that electron cloud can be found this area and beyond that Bohr radius. Okay, so here electron when tries to go this side, a attracting force induced along this line, and that attracting force tries to take the electron to its mean position. Likewise, whenever the electron tries to go towards the nucleus, the nuclear force repels and it moves again outward from the nucleus. In this way the electron fluctuates or vibrates, we can say vibrates about its mean position, means exactly at the so-called Bohr radius, that is A0. So about its Bohr radius the electron is fluctuating or vibrating. This is one model also you can imagine. So what will be the energy at this position? What will be the energy for this molecule? What will be the energy? What can be the energy? Suppose I am going to give from the outside some external heat energy I given. So is the vibrational energy is going to be increased? Suppose initially it is 5. Then if this diatomic molecule taken outside from some energy, then the energy will be 5 and then increase to 6 or 7 or 8, what it will be? That means how the energy is going to be changes if the diatomic molecule or any oscillator, or this is so called, these are called the quantum oscillators energy changes. And we know that h psi is equal to E psi, and in our previous video we saw that for a one dimensional harmonic oscillator the energy eigenvalues are different for different states, and energy eigen functions are also different, psi 1, psi 2, psi 3, like this. That means if I am going to apply h cap psi 1, I am going to find E1 psi 1, and h cap psi 2 I will get E2 psi 2. That means the corresponding eigen function of this energy level is psi 1, and its corresponding energy eigenvalue is E1. Okay, so if we got suppose this is our harmonic oscillator, and we found the minimum energy state having the wave function is psi 1. Suppose that means only I will be apply h cap psi 1, it will be give E1 psi 1. Okay, so for higher excited state, and we suppose we can found that psi 2 will be the second higher excited states eigen function, then eigenvalue will be considered the eigen value equation, then it will be E2 psi 2. So from this dynamics, or by solving this dynamics, we can found the energy states of the diatomic or of oscillator in the quantum mechanics, and energy levels, and so on and so. So now we are going to be discuss in detail about this linear harmonic oscillator. So whatever I have been discussed just now, the same thing I have been written over here. You just watch. I'm just reading those things. Okay, simple things. A linear harmonic oscillator is a point particle attracted towards a fixed center by a force proportional to the displacement of the particle from the fixed center, whatever we have been discussed in this figure. It will be better, I suggest that you draw this figure here. It will be better for you. So this is the spring, and this is the mass, and this is x is equal to 0, and this is the situation A, and this is the situation B. Let this distance is dx, like this. You just draw this figure, it will be better. Okay, and if displacement will be this side, the restoring force direction will be this side. That things we discussed. Only you just draw this figure, it will be help you to communicate these lines. Okay, towards a fixed center by a force proportional to the displacement of the particle. Okay, from the fixed center, and let the motion is considered along x-axis. We consider this motion along x-axis with the origin at the force center. Then this is the force center, and the force is given by the so-called restoring force is directly proportional to minus x. Okay, minus x. Here it is written, particle attracted towards fixed center by the force proportional to the displacement. Towards the fixed center means if displacement is this direction, the force is towards this direction. If displacement is this direction, the force is towards this direction. That means the force is acting on the body, it attracts towards the starting point or mean position. So as displacement and the force are directed opposite with each other and proportional to with each other, that if I am going to be increase the displacement, the induced magnitude of induced restoring force also will be increased. Hence restoring force proportional to the minus x, and restoring force is equal to minus kx. Here k is the force constant. Now the potential energy dVx del Vx will be stored for a displacement dx. Now I am going to be displaced this mass from 0, from x is equal to 0 to x is equal to a, from 0 to a point, what is the distance? Suppose this is the dx distance. So how much energy will be stored? That is nothing but the how much I have to do the work done to displace this mass from here to here. How much work I have to do against this restoring force, that much energy is going to be stored as a potential energy inside this spring. So now potential energy, let dvx, small dvx, will be stored for a displacement dx will be or work done against the restoring force, that is dvx, small potential energy is nothing but restoring force dot dx. Both are opposite with each other, that means angle between them is 180 degree. So total potential energy stored for the displacement x will be, now this is the potential energy as for small distance. Suppose we have to consider this distance 0 to b is the x distance, then how much potential energy is going to be stored? That will be integration over 0 to v, this is dvx and dvx. Here x is the function of v, and 0 to x, displacement 0 to x, restoring force dot dx is equal to 0 to x f restoring force dx cos 180. Dot product, if we are going to consider both the vectors, then both the vectors are opposite with each other, so 180. So 180 is minus, and restoring force magnitude, the restoring force magnitude we know that minus kx, so this is minus kx into dx and integrating over 0 to x, so it is the total dv value will be vx, and here 0 to x, the displacement from 0 to x, okay, from 0 to x, so 0 to x kx dx, that will be half kx square, 0 to x, that is half kx square. So this is the equation of the parabola, that means if we have to increase x, positive x along positive x-axis direction, then the curve will be this one. Along the negative x-axis direction also the variation will be same. That means it is symmetric about the y-axis. Okay, now we have to consider equation number 1. This is equation number 1, and now here we are going to consider the Newtonian formula, that is mass into acceleration. Force is converted or can be written as mass into acceleration form, d square x by dt square is equal to minus kx, and m d square x by dt square plus kx equal to 0, and d square x by dt square plus k by m equal to 0, and this will be we consider k by m is nothing but omega square, and k is nothing but m omega square. Omega is considered as k by m root over, and k is considered as m omega square. Hence equation number 2, okay, here I don't not written, this is equation number 2, you just write this is equation number 2. Okay, so now if I am going to put instead of k is equal to m omega square, then equation number 2, this equation number 2 will be half m omega square x square, let it is equation number 3, and if I am going to consider v minus x, will be equal to vx, that is let equation number 4. From this we found that this is symmetric about both the sides. So from equation number 3 and 4 it is found that the potential energy is continuous, there is no discontinuous, potential energy continuous and symmetric function of x. Symmetric function of x means as plus x I will be increase, then what is the behavior of the potential energy? If I will be decrease the x or I will be move along negative x-axis direction, then also the behavior will be same, because it is half m omega square x square, half m omega square x square, that means it is the nature of the parabolic. So now as shown in the figure, this one. Okay, now as I told that whatever the energy is going to be stored as a potential energy, that will be converted to the kinetic energy. That means whenever a particle in motion, it has in a force, in a force field, if a particle is motion means it has both the energy always. That is one kinetic energy and one potential energy. Force will be there means there will be a potential energy or potential, you can see, you can say whatever we studied in our last topic, that is your one dimensional infinite small potential will. But if there is no force, there is no potential energy. So here, as we consider that the particle is in motion in a attractive force which is proportional to the displacement, so it has two energy. One is kinetic energy and potential energy. So potential energy we found that half m omega square x square, that is equation number 4. Now if we are going to consider the total energy operator of this particle, or total energy or Hamiltonian of the oscillating particle is how much? This will be px square by 2m plus half m omega square x square. Or the Hamiltonian operator I can write hx cap is equal to px cap square by 2m plus half m omega square x cap square. So this will be useful, or this will be applied further for finding the energy eigen equation of this motion or of this dynamics. So the total energy of the oscillating particle is nothing but, this is the part of the kinetic energy and this is the potential energy, or the so-called Hamiltonian operator is h cap x px cap square equal by 2m plus half m omega square x cap square. Now by using this operator, we can, or we are going to be solve, or we are going to be found out the energy eigenvalue equation and its solutions. So we know that you put it the heading, okay. The energy eigenvalue equation in general is nothing but h cap psi x is equal to E psi x, okay. For this situation, h cap is how much? The kinetic energy operator, that is px cap square by 2m plus potential energy operator for this motion. This is the potential energy operator, half m omega square x cap square psi x is equal to E psi x. Here we know that px cap is how much? I minus I h cross del by del x, right? Px cap square is how much? This will be the minus this will be the minus I square h cross square del square by del x square. So it will be I square h cross square del square by del x square. So it will be minus h cross square by del square del x square, that we know. So it will be px cap square by 2m, or we can write minus h cross square by 2m del square psi by del x square plus half m omega square x square psi x is equal to E psi x, okay. So rewriting this above equation by taking this one, E psi x to the left side, we can get in this form, del square psi x by del x square, or you can write in this way, that d square psi x by dx square plus 2m by h cross square E minus half m omega square x square psi x is equal to 0. So some books they have written in the del format and d format. So should not be worried about that. This is the double derivative. Okay, and this is equation number 5. You just consider, or you just recall the time independent Schrodinger equation. What is the time independent Schrodinger equation? That d square psi dx square plus 2m by h cross square e minus vx psi is equal to 0. Whenever a particle is moving in a time independent force field, this is the Schrodinger equation, one dimensional Schrodinger equation. So if you can compare this equation with this equation, what we are going to find? We found that both are same, both are similar, or we can say same, because here del square psi x by del x square, or d square psi x by dx square plus 2m by h cross square, e is there, and vx, here vx is the arbitrary, we have been taken in generalized form, but for the oscillation, for this linear harmonic oscillator, we found that vx have the particular value, that is half m omega square x square psi x equal to 0. So this is the typical second order differential equation from which we can get eigenvalues, eigen functions, means all the physical behavior can be extracted from this equation. This is the so-called Schrodinger equation of the linear harmonic oscillator. So we know that from the Schrodinger equation, if we can solve, then we can identify, or we can predict, or we can estimate all the physical characteristics of a dynamics. So this is nothing but the Schrodinger equation of the linear harmonic oscillator. So whenever we are going to solve, that means if we can found psi x, from the psi x we can determine the what type of behavior of the oscillation, of the quantum oscillation, what type of behavior of the quantum oscillation and its other physical properties. Okay, so now we have to move for solving the equation number 5. To solve the equation number 5, see what I am going to do. This is in very we can say that this is the one type of second order differential equation with variable coefficient. See here x is there, means this term is variable, so it is a variable coefficient of second order differential equation. So I am trying to be reform, or I am going to transform to another form which will be easy to solve. So only for that, here to solve the equation number 5, we considered a dimensional less variable as y equal to m omega by h cross to the power 1 by 2 or root over into x. Let it is equation number 5i. Then d by dx can be written as dy by dx into d by dy. So that implies d by dx will be dy by dx. Dy by dx will be how much? This is the constant, and this constant dy by dx will be how much? This much. So if y equal to this much, dy by dx will be this much, because here it is only x. So d by dx will be dy by dx. Dy by dx we found this much into dy by dy, and d square by dx square we can found m omega by h cross d square by dy square. So here now substitute d by dx and d square by dx square, the value whatever we found here, d by dx we found this one, d square by dx square we found this one. These two values I am going to be substitute in equation number 5 to simplification. Okay, so here this is equation number 5. D square by dx square, instead of d square by dx square, what I am going to be put? I am going to be put m omega h cross d square by dy square. So m omega by h cross d square by dy square psi y, because as it is transformed from x, it is psi x, as it is transformed to y, so it will be psi y plus 2me by h cross square is there, 2me by h cross square minus, you can see here it will be m square omega square by h cross square into h cross by omega into y square. See, it is half m omega square x square. Okay, so if we are going to consider x from here x is equal to how much it will be? It will be y into h cross by m omega, right? And x square will be root over it will be y into h cross by m omega. X square is equal to y square into h cross by m omega. So here we found x square equal to y square into h cross by m omega. Now see, here 2m by h cross square into e, here 2me by h cross square, then 2m by h cross square into this term, 2 got cancel, m into m square by h cross square, omega square into x square. So m square omega square by h cross square into x square means this much, that is y square h cross by m omega, y square h cross by m omega into psi y equal to 0. Now m omega by h cross d square psi y by dy square plus here m omega got cancel, h cross got cancel. Now you can take m omega by h cross outside, then it will be here, see, m by h cross square, so m by h cross square omega is not there, so obviously it will divide, so 2e by h cross omega minus y square psi y equal to 0, because here m omega got cancelled, m omega h cross is taken outside, it will be, see, it will be 2e m by h cross and omega also taken outside, m omega by h cross, so it will be 2e by h cross omega minus y square psi y equal to 0. Let it is equation number 6. Now from this two term we are going to take m omega h cross common, so m omega by h cross taken outside, it will be d square psi y by dy square plus 2e by h cross omega minus y square psi y equal to 0. Okay, since m omega by h cross square not to be 0, so the equation number 6 will be, another part should have to be 0. Okay, so this will be equal to 0, this will be equal to 0. See, here I written simple mistake, that this bracket will be here. Okay, this bracket will be here, d square psi y by dy square plus 2m h cross omega minus y square psi y equal to 0. Correctly, you just pause the video and you have to write the note. Again, I am going to be suggest you that you have to write the note, because note is always useful for your exam. So now, if this will be not 0, so how is this equation is going to be satisfied? This should have to be 0. This bracket term is going to be 0. So d square psi y by dy square plus 2e by h cross omega minus y square psi y is equal to 0. And let consider lambda as 2e by h cross omega. You just remember this term. This will be required in our preceding sections, preceding discussions. So psi, here lambda is consider as 2e by h cross omega. So put instead of 2e by h cross omega lambda, so this will be the equation number 7. So we found, or we just transformed for our to solve this equation easily, we transform this one to this one. So because by using this equation number 7, we can estimate or we can predict what will be the behavior of psi at the infinite. At the infinite, when y tends to infinite, what will the value of psi, that we can predict by using equation number 7. Okay, and also this equation number 7 is also the general differential equation of the this harmonic oscillator, and this equation found from this original equation. Okay, only just we have been transformed this equation to this equation. Now we are going to consider asymptotic behavior of the psi x, asymptotic behavior of the psi x. Actually not psi x, it will be psi y. Now before we have to find out the complete solution of equation number 7, it needs to analyze the behavior of the solution in the asymptotic region. That means when y tends to plus or minus infinity, what will be the value of psi y? That should have to be considerable, because that is also nothing but is our boundary condition, because at plus or minus infinity psi should have to be 0. Okay, that condition should have to be satisfied by a wave function what we are going to be solve for the equation number 7. So only for that we are considered asymptotic behavior of psi y. As y tends to infinite, suppose we are going to consider y tends to infinite, this y square will be greater than that of the lambda. So you see, you just see. Now we are going to consider y will be infinite. This y tends to infinite. Okay, y tends to infinite. If y tends to infinite, lambda is the value of 2e by h cross omega. E is somewhat a definite energy value and h cross omega are the two constant values. So this could not be infinitive, but y square, if it will be infinite, then this will be greater than that of the lambda. Hence when y tends to infinite, this will be negligible. So equation number 7 can be written as, this thing is written only as y tends to infinite, y square greater than that of the lambda for any finite value of energy E. The dimensionless variable lambda is negligible as compared with y square. Okay, so the equation number 7 is reduced to d square psi infinity y by dy square minus y square psi infinity y equal to 0. Here infinite symbol is in subscript, because as we are considering y tends to infinite, only for that psi subscript of infinite I have been written. Okay, this is only one naming we can say, only we given the name of the psi, that at y tends to infinite, this is the name. So equation number 7 will be in this form. Let this is equation number 8. Okay, so that is minus y square psi infinite y equal to 0. Let this is equation number 8, and this is a second order differential equation, and let its trial solution is e to the power beta y square, because in general the solution of this type of equation will be in the form of this one. So let the trial solution of this equation number 8 is equal to psi infinite y equal to e to the power beta y square. So then first derivative of this one will be 2 beta y e to the beta y square. Second derivative will be this much. Okay, if I will compare this and this, here you can see beta square y square is there. So this will be negligible as compared to this one. So I consider that this second derivative of this one is approximately this much, 4 beta square y square e to the power beta y square. Now the equation number 8 will be, I have to just put, instead of d square psi infinite by dy square and psi infinite y, so it will be 4 beta square y square e to the power beta y square, 4 beta square y square e to the power beta y square minus y square into e to the power beta y square equal to 0, and that will be 4 beta square minus 1 y square into e to the power beta y square equal to 0. That implies 4 beta square minus 1 equal to 0, and beta is equal to plus or minus 1 by 2. Thus asymptotically the solution will be how much? Psi infinite y will be approximately e to the power plus or minus y square by 2, plus or minus half y square or y square by 2. So here you can see one interesting thing is that, but the solution must be, so here at infinite, this psi, at infinite psi, what is the meaning of this one? Psi infinite y means at infinite, when y tends to infinite, this is the value, will be, we are going to consider e to the power plus 1 by 2 y square or e to the power minus 1 by 2 y square. But we know that as y tends to infinite, at infinite, the psi should have to be 0. The psi should have to 0. This is our boundary condition. We know that. So, but the solution must be finite everywhere and satisfy the condition as psi tends to 0, y tends to plus or minus infinity. That means y tends to either plus infinity or minus infinity. Psi should have to 0. Psi should have to 0, psi tends to 0. So this is our bounded condition, we know that one. So satisfy the condition that psi infinite y tends to 0 when when y tends to plus or minus infinity. That is the bounded condition. But if we are going to consider the solution is this one, psi infinite y e to the power half y square, if we are going to consider, then what will happen? If y tends to 0, this will be increases. That means this is diverge our from our boundary condition, because see, if y tends to infinite, if I am going to increase the y, then it is continuously increases. But the condition is that it has to satisfy that y tends to plus or minus infinity, psi y should have to be 0. But here it is diverge as y tends to infinite. So this solution not to be acceptable, then rest one is going to be acceptable. Now the general solution of the equation number 8 will be psi y will be equal to, the general solution will be psi y will be equal to, or psi infinite, you can write, I not written over here because you have to accept that it is infinite. The general solution of equation number 8 will be psi y equal to fy, some constant with some variable into e to the power minus y square by 2, because plus y square by 2 is not going to be considered, only minus y square by 2 has to be accepted. This is equation number 9. Now you just see this equation, how we found when we consider y tends to infinite for the equation number 7. When y tends to infinite, we found the equation number 8. So whatever the solution for the equation number 8, that will be also the solution of equation number 7. So here we got the solution from equation number 8, from equation number 8 by considering the boundary condition, that is equation number 9, this one. Now we are going to find out dy by d psi by dy will be this much. First derivative of this one. First derivative of this one means first you differentiate this one, and this will be consider the product formula, df by dy into e to the minus y square by 2 plus f into derivative of this one, it will be minus 2y by 2 into e to the minus y square by 2. And so d psi by dy will be this much. Similarly, here you just pause the video and you follow the steps and you write the steps. I am not going to be explain for this derivative. This is a simple derivative like that. This is the d psi by dy, and similarly d square psi by dy square will be equal to this much. You just follow up, okay, and or here u to the power y square by 2, e to the power minus y square by 2, minus y square by 2, minus y square by 2 taken outside, and it will be d square f by dy square, and here you can see df by dy into y, here minus also y df by dy, so minus 2y df by dy plus, here you can see minus fy square, sorry, see here you can found that minus minus plus fy square, and it is minus f, you can take f is common, it will be y square minus 1 and e to the minus y square by 2. So this is the second derivative and this is the first derivative. Now we are going to use this, or we are going to put this value and this value in equation number 7, because I told that equation number 8 we found from the equation number 7 by considering the asymptotic behavior. So as this is the solution of equation number 8, this also be the solution of equation number 7. So these two values, the first derivative and second derivative, if we are going to put in equation number 7, carefully watch, carefully just watch, d square psi by dy square I am going to put in equation number 7. You just simply this much I have been substituted, then this one I have been substituted, so it will be d square f by dy square minus 2y df by dy plus fy square minus 1, okay, then it will be and here d square psi by dy square I have been substituted, then psi y is how much, fy into e to the power minus y square by 2. So I just substituted f, that is f e to the power minus y square, okay, f, this is, see, f e to the minus y square I have to just substitute over here, it will psi minus y square, psi minus y square, psi minus y square, see, sorry, psi I told, lambda minus y square into f into e to the minus y square by 2, okay. So by substituting this value and this value in equation number 7, we found this one, okay. So this will be d square f by dy square minus 2y df by dy, here you can see f y square, and this is minus f y square, got cancel, it is minus f and plus fy, it can be written as fy lambda, this is lambda, f lambda, so lambda minus 1 into f into e to the minus y square by 2 is equal to 0, okay. So but this could not be 0, okay, this is the variation term, this could not be 0. To satisfy this equation, this coefficient should have to be 0, that will be d square f by dy square minus 2y df by dy plus lambda minus 1 f equal to 0. Let this equation number is 10, let this equation number is 10. This is called as second order differential equation having variable coefficient, and the solution of this equation can be found or can be solved by power series method, okay. So this equation number 10, this is equation number 10, is called as the second order differential equation having variable coefficient. Now this can be solved by the power series method, can be solved by the power series method. So now power series solution, okay, yes, so this is the another format, this equation is the another format of equation number 7, okay. So the equation number 7 is transformed to this type of solution to solve in the way of the power series method, okay. Now The power series solution of the differential equation 10 can be written in the form of the power series as Fy equal to summation over s is equal to 0 to infinity as y to the power s. Let it is equation number 11. Let it is equation number 11. And its first derivative will be s into as into y to the power s minus 1. S is equal to 1 to infinity would not be put as 0 because if I am going to consider 0, then this term will be 0. Okay, so this is equation number 12, and it is varies from 1 to infinity. Like that, double derivative will be equal to s equal to 2 to infinity summation over s equal to 2, sorry, s into s minus 1 as e to the power s minus 2. Okay, so for this also could not be acceptable 0. It will be, this term will be 0. If I will be put 1, it will be 0. So only for that it will vary from 2 to infinity. So substituting the equations 11, 12, 13 in equation number 10, what we are going to get, just I am going to put these values in equation number 10. Okay, simple I am going to put. What I am going to get, this is summation over s is equal to 2 to infinity s into s minus 1 into as into y to the s minus 2 minus 2y. S is equal to 1 to infinity. Here 2y is there already. It is 2y is there here. Okay, in equation number 2y is there. So only we have to put df by dy. Df by dy is the value of this one. I substituted. Then plus lambda minus 1 fy. Lambda minus 1. See, lambda minus 1 into fy. I have to be substitute, and this will be equal to 0. Right now, see, this is y is here and this is y to the power s minus 1. So it will be y to the power s, and this term as usual I have been written. It is this term and this term is same, and here y is cancelled out and it will be y to the power s, and this term is also this one equal to 0. Now to maintain the uniformity, here you can see the here summation is started from s is equal to 2 to infinity, 1 to infinity, here 0 to infinity. To maintain the uniformity of the summation, put s is equal to s dash plus 2 in the first term and s is equal to s dash for second term and third term respectively. And then what we are going to get, see, now here I am going to put s is equal to s dash plus 2. If I am going to put see, s dash plus 2 is equal to 2, s is equal to s dash plus 2 is equal to 2, then s dash will be how much? 0. So s dash equal to 0 to infinity, and minus 2, and all the terms are there. And here s, instead of s I have to put s dash plus 2, and here it will be s dash plus 1, because s dash plus 2 minus 1, it will be s dash plus 1, a s dash plus 2. Here a subscript of s, instead of s it will be s dash plus 2 y to the power s dash minus 2 summation over s dash 0 to infinity s dash into a s dash into y to the power s dash plus lambda minus 1 summation over s dash equal to 0 to infinity a, this is a subscript, okay, s dash into y to the power s dash equal to 0. Okay, now s dash equal to 0 to infinity, you just you just here y to the power s dash is common for all the terms taken outside. So it will be the remaining terms are here summation are uniform, so summation can be right at the initial for all the terms. So summation over s dash 0 to infinity, here s dash plus 2 into s dash plus 1 into a s dash plus 2 minus 2 s dash a s dash 2 s dash a s dash, here also a s dash is common factor, so s dash taken out outside, and it will be minus 2 s dash, and this will be minus means it will be, this will plus and this is minus, so minus taken outside means this will be 2 s dash plus 1 minus lambda a s dash e to the power s dash equal to 0. Okay, just I have been taken outside this term a s dash from these two term, and written by taken minus as common from these two terms. This will be written as equation number 14. As equation number 14 obeyed for any value of y, then coefficient of every power of y must vanish. That means if this equation will be satisfied, then for every power means for every s dash value, this should have to be vanish. So that implies the coefficient of equation number 14 should have to be 0, that is s dash plus 1, s dash plus 2, a s dash plus 2. This is subscript, okay. A s dash plus 2 is a subscript, minus 2 s dash plus 1 minus lambda a s dash into a s dash equal to 0. So it can be written as a s dash plus 2 will be equal to 2 s dash plus 1 minus lambda divided by s dash plus 1 into s dash plus 2 a s dash. This is called as the recursion relation or recursion formula. For further simplification, only see here s dash is there. So sometimes you can forget to put s dash. So it will be somewhat difficult to be write always dash. So for the simplification or for the simplified manner, if we are going to write this above equation number 15 by considering s dash equal to n, I just considered s dash equal to n. Just you can say I just changed the name only, nothing else. So s dash equal to n, the equation number 15 can be rewrite as here a s dash as n, a n plus 2 is equal to 2n plus 1 minus lambda divided by n plus 2 into n plus 1 into n plus 2 into a n. Okay, so a n plus 2 divided by a n taken out this side, a n plus 2 by a n is equal to this much, 2n plus 1 minus lambda divided by 2n plus 1 n plus 2. Now you consider n tends to infinite, what will be its value? See, first of all you consider the numerator. Here lambda, I told that time, lambda is nothing but 2e by h cross omega. Lambda is nothing but 2e by h cross omega. You just remember at the time of writing equation number 7, I just substituted, instead of 2e by h cross omega, I substituted the lambda. So here lambda is the term belongs to energy. So for particular value of energy, lambda will be a finite value. Yes or no? Lambda will be finite. Okay. Now you consider n tends to infinite. If n tends to infinite, then this value 1 and this lambda is going to be neglected as compared with this term. Likewise, if n will be infinite, then 1 will be neglected as compared with this one, and 2 will be neglected as compared with this one. So this term will be nothing but how much? 2n by n square approximately, right? Because this 1 and lambda can be neglected, 1 and 2 can be neglected, so it will be, numerator will be 2n and denominator will be how much? N into n square. So limit n tends to infinity, a n plus 2 by a n approximately how much? Here n got cancelled with another n, it will be 2 by n. Let this is equation number 17 at n tends to infinite. For n tends to infinite, a n plus 2, this one value is approximately 2 by n. Here is the another interesting things we can observe over here. First, we have to consider the expansion of ey square. Okay, expansion of ey square. We know that expansion of ey, see, expansion of ey, generally expansion of ey is what? Or e to the power x, that is 1 plus y by 1 factorial, y square by 2 factorial, y cube by 3 factorial, y 4 by 4 factorial, where n is equal to 0, 1, 2, 3, 4 like this. So here if we are going to consider y square, then it will be 1 plus, instead of y it will be y square by 1 factorial, y 4 by 2 factorial, y 6 by 3 factorial. So in generalized, what we are going to write? In generalized, what we are going to write? You just see. Wherever we are going to take the two terms, it will be in this form. See, this term is belongs to this one. N here, yes, here n equal to 0, 2, 4, 6, 8, 10 like this. So here n is what? 4. N is 4. So y to the power 4 and 4 by 2 is factorial. And just nearby another term is nothing but we have to consider, if we are going to consider as n equal to 2, then just nearby term will be n plus just nearby term means, see, n plus 2, here n is equal to 4, 4 plus 2 is equal to how much? 6 is there, and here 4 by 2 plus 1, 4 by 2 is 2 plus 1, 3 factor. Wherever you have to consider, the nearby terms will be match with this one. Okay, you just consider these two terms considering as n is equal to 8. So n is equal to 8 means y to the power 8 divided by 4 factorial. Okay, divided by 4 factorial. Then n is equal to 8. 8 plus 2 is equal to 10 by 8 by 2 equal to 5 plus 1 is 5 factorial. So this series is in generalized intermediate to 2 terms we can get this one. That means these 2 terms, if is going to be continuously repeated, we are going to get this series. Only for that we have been written that e to the power y square is equal to 1 plus y square plus y to the power 4. Here you can write another term, y is 6 to the power 3 factorial. That's it. Plus y to the power n by 2 factorial. How it is, I told that one. You just watch going back the video. Plus y to the power n plus 2 by n by 2 plus 1 factorial. These two terms, if you are going to repeat this side, then you are going to consider, you can found this one. Okay, here n is, here I not written, here an is 0, 1, 2, 3, 4, sorry, 0, 2, 4, 6, 8, 10 like this. Now you consider 0. If you are consider 0, then y to the power 0 equal to 1. 0 plus 2, 2, and 0 to y square by 1 factorial, like that. So so 1 is considered as b0, b2 y square, b4 y to the power 4, and this is bn. Bn is considered as 1 by n by 2 factorial. Bn is considered 1 by n by 2 factorial. Bn plus 2 is considered as 1 by n by 2 plus 1 factorial. Okay, for this series. Here n equal to this one. So now bn plus 2 by bn, if we are going to consider bn plus 2 by bn, will be how much? See, bn plus 2 is n by 2 plus 1 factorial divided by n by 2 factorial bn. Okay, sorry, the bn plus 2 is 1 by n plus 2 factorial. This is 1 by n by 2 factorial. So this will be nothing but how much? This will be n by 2 factorial by n by 2 plus 1 factorial. That means it will be 1 by, see, n by 2 factorial divided by n by 2 plus 1 factorial. That means 1 by n by 2 plus 1. Because see, 5 factorial by 6 factorial is how much? 5, like that. N by 2 factorial divided by n by 2 plus 1 factorial means it will 1 by n by 2 plus 1 factorial. Now consider n tends to infinite. If n tends to infinite, bn plus 2 by bn, here n plus 2 and n both are subscript. Okay, so bn plus 2 by bn is approximately how much? You see, when n tends to infinite, this will be neglected, this 1 will be neglected, though we are going to get 1 by n by 2, that will be 2 by n. So when n tends to infinite or n is very large, this value is going to get 2 by n let this is equation number 8. Let this is equation number 18. Let this is equation number 18. So now from equation number 17 and 18, you just compare equation number 17 and 18. Okay, equation number 17 right hand side 2 by n, equation number 18 2 by n when n tends to infinite. That means n tends to infinite. See here, fy, this is the this 2 by n value we got by considering what? Fy, by considering the power series solution of this one, right? Now this also, this 2 by n we got if we are consider that e to the power y square. The expansion of e to the power y square, if we are going to consider, we are going to get, we got also 2 by n value. Equation number 18, that is equation number 18. So equation number 17 and 18, if we are going to compare that, we can found the f, or here the power series solution fy will be equivalent to what? Will be equivalent to e to the power y square. See, from e to the power y square we found 2 by n. Okay, from the power series solution whenever I solved from the power series solution whenever I solved from fy, also I got 2 by n. So here we can consider that the so called power series solution will be equivalent to e to the power y square. So from equation number 17 and 18, here in the back page it is. So in the next page, from equation number 17 and 18, it has been observed that if n is large, that means n tends to infinite, fy behaves as e to the power y square. Okay, so psi y will be how much? Psi y will be how much? Where is the psi y we have? See, here is the psi y. Psi y is here, equation number 9. Equation number 9, we have fy e to the power minus y square by 2. This is the psi y. So now this psi y will be how much? If fy we are going to consider e to the power y square by 2, then psi y will be approximately e to the power y square by 2, e to the power y square into, by considering fy is equal to e to the power y square, e to the power y square into e to the power minus y square by 2. So e to the power y square into e to the power minus y square by 2. Or so this is e to the power y square by 2, this is minus y square by 2. So it will be psi y is approximately e to the power y square by 2, which diverges as y tends to plus or minus infinite. It can be diverge when y tends to plus or minus infinite. So this makes psi y as unacceptable wave function. Okay, so psi y we considered by the power series method that it will be approximately e to the power y square. But if we are going to consider this one, it will diverge at y equal to plus or minus infinity. So psi y can be acceptable? It could not be acceptable. So it will be unacceptable wave function. So for physical acceptable wave function, what we are going to do? For physical acceptable wave function or the solution, psi must be terminate after a finite number of terms. Are you got the point? Here, after solving by the power series method, we found psi y equal to e to the power y square by 2. But it will be diverge when y tends to plus or minus infinity. So it could not be acceptable. So for physical acceptable, it has to be terminate. It has to be terminate to a particular finite, after finite number. Means after finite number it has to be terminate. So that fy must terminate. Fy, that fy is this one. Fy must terminate after a finite number of terms and reduce fy to a polynomial. Fy to a polynomial. Okay. So what we found? for the acceptable solution, fy should have to be terminate after finite number of terms. See here, psi y was in equation number 8, equation number 9. This is the general form, y fy into e to the y square by 2, right? So here, if we are considering fy is equal to e to the y square, then it will be in the form of e to the y square by 2. So here fy is equal to e to the power y square is creating the problem. So if we are considering fy is equal to this much, then it is not satisfy the boundary condition. It is diverges, so it could not be acceptable. So psi y has to be acceptable. This fy should have to terminate after some finite number of terms, okay, and reduce to fy to a polynomial. Suppose the series terminates at nth term. Let this series is terminates at nth term. If nth term it is terminates, that means nth term value an will be not equal to 0. See, from this equation, if at nth term it will terminate, the coefficient of an is not going to be 0, but after nth term an plus 1, an plus 1, an plus 2, these values is going to be 0. Okay, so if we are going to consider equation number 16, and to acceptable the wave function, we consider that the series terminates are at nth term, then an not to be 0, but an plus 2 is equal to 0. Then equation number 16 will be how much we are going to get. See, in equation number 16, an is not equal to 0. This will be 0. That means this value is going to be 0. So that implies 0 equal to 2n plus 1 lambda by 2n plus 1 into n minus n plus 2. That implies 2n plus 1 minus lambda equal to 0, or lambda equal to 2n plus 1. Here n is equal to 0, 1, 2 dot dot and so on. Here as it is n, and we know that lambda is equal to 2e by h cross omega. We already know this one. Okay, if we have to put instead of lambda 2e by h cross omega, then e will be nothing but will be not one value. As it is n, it can be written as 2en by h cross omega is equal to 2n plus 1, or en equal to n plus 1 by 2 h cross omega. Let it is equation number 19, where n is equal to 0, 1, 2 like this. So what we found, these equation number 9, for each value of n, we are going to get the energy eigenvalue of this linear harmonic oscillator. So for n is equal to 0, you put n is equal to 0, E0 is equal to h cross omega, n is equal to 1, it will be 1 plus 1 by 2, 3 by 2 h cross omega, 2, it will be 5 by 2 h cross omega, 3, if you are going to put 3, if you are going to put 3, it will be E3 is equal to 7 by 2 h cross omega. So, and differentiation, if you are going to differentiate the conjugative energy values, it will be h cross omega. See, En minus 1, conjugative to energy levels value is h cross omega. So from equation number 19, we found even at n is equal to 0, E0 have some value. That means at ground state or equilibrium state, there is a energy, vibrational energy. So that have some these things will be follow to the Heisenberg uncertainty principle that we are going to be discussed later. But here what we found, this will be nothing but your variation of potential, this one. And for each value of n, we found the discrete energy levels. For n is equal to 0, E0 is equal to h cross omega by 2. For n is equal to 1, this will be E1 equal to 3 by 2 h cross omega, and n equal to, this will be 5 by 2 h cross omega, and in between the two level, the difference is h cross omega. Means equally spaced discrete energy level we are going to get for the linear harmonic oscillator. So the same thing from the above, we found that En minus 1 is equal to h cross omega, is equal to h cross omega. So we found that from equation number 19, we found the discrete energy levels are possible for the linear harmonic oscillator, but the energy gap between the two energy level are same always. So the equation number 19 and 20 provide the information that energy eigenvalues of a particle moving in a linear oscillation form an equispaced discrete spectrum. Here spectrum means energy levels, discrete energy levels, but equispaced. Okay, so in the next, then we have to discuss eigen function. Okay, now substituting here, we found that lambda equal to 2n plus 1. If this lambda is going to be substitute to the in the equation number 10, in the equation number 10, we can get this equation. This is exact differential equation of Harmonic differential equation. So as it is a Harmonic differential equation, then its solutions will be matched with the Harmonic differential equation, and we are going to be write in that way. That we are going to discuss in our next class. So in our next class, we are going to discuss about eigen functions. So next class we are going to discuss. See, here we found that what? We found the each energy states, each stationary energy states. That means each energy state have its own eigenvalue, eigen functions, means wave functions. So what is the wave function for each energy states? That we are going to be derive in our next class, and I am going to show you that it is so interesting that this is the figures that for first energy state, this is the ground state energy. The wave function is this one, and the second excited state for n is equal to 1, and third, fourth, like this. So these are the wave functions, representation of the wave function, and these are the so-called probability density that we are going to discuss in our next class in detail. And here I am going to be say to you one thing, that even if n is equal to 0, E0 equal to h cross omega. That means at equilibrium position, or very at the ground state itself, the particle have some energy, means they are in the vibrational state, which follow the Heisenberg uncertainty principle. How it will follow the Heisenberg uncertainty principle, that also we are going to discuss next class. Okay, this is ground state, lowest energy state, follow the uncertainty principle. That also we are going to discuss the next class. So here I really suggest that you go through this video properly, pause the video, write down the notes, and here I written many things in the pencils at the time of explain. So may you can write for your understanding purposes, but I think so, as your wish you can write, but I suggest that you write properly the notes, which will be useful for your exam. Okay, so thank you so much for watching this video. In the next video we are going to discuss about eigen functions. Okay, so thank you so much for watching this video. Thank you.